but I'd put a lot more effort into the back-end code generation stuff. Okay? You guys know this too, but it's worth going over. You don't want the compiler error messages to be in terms of things the compiler understands. Right? I mean, yeah, there's a conflict in hash bucket 53. That's great, and I'm sure that's a true statement, but it doesn't mean a whole lot to the user. Error messages should refer to the source program. For C++, that's not so much of an issue. But every so often, it's interesting, every so often I see someone who will have error messages that make sense to the programmer, not to the end user. So you have to put yourself in the end user's shoes. Before assignment 2 was due, a few people would stop by my office and say, how much error recovery do you want me to do? What do my error messages need to look like? Because the spec is vague on these things. Is it enough to say this? Is it enough to say that? Should I also say this? Is it okay if I don't say that? And my response to them is, look, if you were paying for that compiler, would you use it if it gave you that level of error message? The question really is you have to put yourself in the end user's shoes and say, is that person going to be able to use the compiler with these error messages, right? So that's what you need to think about. They need to refer to the source program. For C++, that's not terribly difficult. But if you're doing full C, for example, and you had includes in them, and you had macros in them, then things become a little bit more complex, right? Because once I've done macro expansion, what the compiler sees is the stuff that happens after macro expansion is done, right? Well, the end user doesn't see the program that way. So if I have macros that span several lines, now my line numbers are all out of whack because CPP has expanded out a whole bunch of stuff. CPP has included a whole bunch of stuff. So somehow, the compiler and the preprocess and all of those things and the macro expansion thing, they need to work in concert so that when the compiler actually gets to an undeclared identifier, which is fairly deep into the compiler pipeline, at that point, and says something like X is redefined or X is undeclared. This all happened after macro expansion and after inclusions and all of that stuff, right? So the error messages still need to make sense with respect to the original source language line number. You guys don't have to worry about this in your project, but it's something to keep in mind because there's some machinery needed to make certain that error messages still make sense, okay? Error messages should, as far as possible, indicate the location and nature of the error. You guys are doing that, right? If you aren't, consider yourself castigated. They should be specific. Okay, they should not be redundant. This is now going to come into play for type errors. Okay, so when does the next one begin today? All right. I can sense the excitement. Maybe the people who aren't, maybe all these people are out there writing code right now as we speak. So I want to spend one minute talking about redundant errors. So imagine a fairly common mistake, which is that you forget to declare an identifier. Or I do this all the time. When I'm typing, sometimes I hit the shift key slightly out of whack when I hit the whatever character. So uppercase and lowercase get thrown off. Sometimes you're cutting and pasting, and not all the declarations go along with the piece of code that you've cut and pasted. So let's suppose that I have a program, and there's a function in which a variable x has not been declared. Okay, for maybe I forgot to declare it, maybe there's a case problem, maybe cutting and pasting, whatever. So your compiler detects that and said, hey, line 5, x is not declared. Then we go on, and on line 6, there's another reference to x. Guess what? X is not declared by now either. Hey, line 6, x is not declared. We go on to line 8. Another reference to x. What are you going to tell the programmer? X is not declared again. You idiot, you haven't declared x third time. So the problem with that is that if I have a page full of x not declared, maybe somewhere buried in there is y not declared. But I'll miss that forest because there's so many x's not declared, right? That'll just get lost in all the noise. Repeating that x is not declared over and over and over and over is not conveying new information. The programmer knows that already after the first error message. So it's not helping the programmer to say, oh, x is not declared. So you need to do something to avoid that redundancy. And that's something that you guys will need to do in your type checking, because you're checking declarations, you're checking types. You shouldn't give redundant error messages. But what exactly do you do? Well, the usual thing that's done is to say when x was first detected as being not declared, you say, OK, I've told you about x not being declared. Now I'm going to pretend that x has been declared and go on from there. So the next time I see x, it'll look like it's been declared, and I won't give you a redundant error message. Question?
What if it's a different scope? So the first time you didn't declare it in the main thing, and then it's in a function.
What if it's in a different scope? You're absolutely right. It could be. So as with syntax errors, semantic errors can also, there isn't a single clear-cut best course of action, which makes it an interesting problem, right? I mean, you get to think about what is a good way to deal with this. Otherwise, it would be a boring assignment. No, I refuse to believe that. You want excitement. Someday you'll be able to write a bestseller, my compiler assignment. We'll skip that. I don't want updates. What time is it? Let's take a real quick 2-minute break and we'll talk about semantic analysis. So all this time you thought programming languages could be dealt with using context-free grammars. I lied to you. You were wrong. I was wrong. So it turns out that context-free grammars are not enough. Okay, so in fact, when I motivated context-free grammars, I said regular languages or regular expressions aren't enough. Well, it turns out that context-free languages, context-free grammars aren't enough either. And one can actually prove this formally. For example, the property that variables must be declared before they are used can be formulated as a simple little language, and one can show that it's not context-free. Okay, so for those of you who are doing automata theory, the way you do that is using some sort of pumping lemma argument, and you can show that this property, appropriately abstracted, is not context-free. So, well, that's a bummer. Now, it turns out that parsing context-sensitive languages, actually, let me back up a little bit. There's something in formal languages called the Chomsky hierarchy of languages. So at the bottom, the simplest is regular languages. Then you have context-free languages. Then you have context-sensitive languages. And then you have what are called general languages. Regular languages are really easy to handle. Context-free languages are a little harder, but still fairly easy in the sense that it's polynomial time. Then there's context-sensitive languages, which are still easy in the sense that they are doable. And general languages are hard in the sense that they're not doable. By not doable, I mean that you need a full-blown Turing machine, which means that certain things become difficult. So one thing that we could imagine doing is to say, OK, not all program properties can be expressed using context-free formulations. So maybe the right thing to do then is to go up. When we notice that some syntactic features, such as balanced parens, arbitrarily nested balanced parens, could not be captured using regular languages, we said, OK, let's go up in the hierarchy and go to context-free languages. And hey, we can handle balanced parens in context-free languages. So maybe the thing we could do is to go up one more level in the Chomsky hierarchy and go to context-sensitive languages. And we could. It turns out that parsing context-sensitive languages is hard. Well, in a matter of speaking. Arbitrary context-sensitive languages are parsed by something called linear bounded automata. And we won't study it, but I mention it in case it comes up in Jeopardy sometime. But here's what makes linear bounded automata or context-sensitive languages computationally expensive. I don't know if you guys have heard of this big NP complete versus P versus NP. NP completeness is hard somehow. Have you heard that idea? So the idea of NP complete is that it's a class of problems that can be solved efficiently in polynomial time using a property of non-determinism in the Turing machine context. Okay, so long story short, the quick summary is that a kind of automata called Turing machines with non-determinism can solve them efficiently. And the big question is, if I don't have non-determinism, can I still solve them efficiently? These guys live in a complexity class called n space, which properly includes NP. Okay? So NP, I'm not writing this well. NP is a subset of these things. So not only is the acceptance problem, is the problem of determining whether a particular input string is in a given context-sensitive grammar. That's at least as hard as NP. And most theoreticians, I don't delve into these things, I kind of look at them from a distance. Most theoreticians believe that this is bigger than NP. Okay, so it's at least as hard as possibly hard. So long story short, we compiler writers who are intrepid but not that intrepid will not deal with linear bounded automata. Okay? So what we'll do instead is to say, you know what? Going to context-sensitive languages doesn't seem like it's worth the cost. It's simply not practical for our purposes. Okay? So what we will do as a pragmatic measure is we'll combine context-free and context-sensitive checking. So what we'll do is we'll use context-free parsing to check the shape of the code. And then we'll have an additional layer that simply checks the context-free properties. Okay, so that's how we'll get by. And then that way we'll stay polynomial time, we'll stay efficient. So it's important and useful to think about what is this deal with NP stuff? I mean, it comes up here and there, and people talk about it. And a lot of computer scientists have this fear of NP completeness. Like it's I don't know, some sort of Friday the 13th bogeyman. It's like, oh my God, it's NP complete. I must run away. So it's important to put these things in context and in proper perspective. If, as is widely believed, if P is not equal to NP, P is the class of problems that can be solved in polynomial time by a deterministic algorithm. Okay? And NP is the class of problems that can be solved in polynomial time, so efficiently, by a non-deterministic algorithm. And it's now widely believed that the two are different, okay, that the two are not the same class. So not everything that is efficiently solvable non-deterministically is also efficiently solvable deterministically. So people say, oh my God, this is NP, it's NP complete or something, so it's hard and therefore I'm dead. That, of course, is complete nonsense. So don't do that. What that means, if in fact NP is not equal to if NP is not equal to P, then what that means is that a problem that is NP complete or NP hard is as hard as any other problem in that class. That is, people believe that will take time, in the worst case, exponential in the size of the input. Okay, And there's sort of this common belief now that P is not equal to NP, so that these hard NP problems probably are exponential time in the worst case. So think of this, okay? If people say, oh my God, this is NP complete, first problem, what does that mean? Well, it means that in the worst case, the time complexity of a deterministic algorithm will be exponential in the size of the input. Worst case. So in compilers, when we're doing compilers, and it turns out that there are many, many problems that are in fact NP complete or NP hard. And like I said, people kind of keel over the minute they see that phrase and say, well, then we can just go home. And they don't ask, okay, what is the worst case? How big do my inputs get in the worst case? So I'll give you an example, okay? I'll give you an example. The problem of register allocation, which is, well, not register allocation, that's not such a good one. Now we can talk about register allocation, why not? So the idea is when I'm doing code generation and I'm doing code optimization, if I can put variables into registers and I can use my registers intelligently, then the quality of the code and the performance of the program improves a lot. Okay, so this is something that is done as part of the code optimization phase. Well, optimal register allocation turns out to be an NP complete problem. So people say, whoa, that's really horrible. But then if you can think about that and say, well, okay, but how big are my register allocation instances? So that's a reasonable question one can ask. And depending on the kind of register allocation you're doing, in certain situations, the problems don't get that big. Okay, they just don't get that big. So I'll give you a specific example. People have looked at register allocation in a whole bunch of different settings. One setting is within code blocks that are something called basic blocks. Okay, so we're doing optimal register allocation within a basic block. Well, in that case, how big does a basic block get? I haven't even told you what a basic block is, but intuitively, it's a sequence of straight line code. And people have done studies, and in most programs, most basic blocks turn out to be of the order, on average, about 4 or 5 or 6 instructions long. You say, wow, for that, I can do an exhaustive search. I mean, it's exponential, so what? 2 to the 5 is, I can handle 2 to the 5, right? So maybe NP complete is not that big a deal in such a situation. So this is a big digression. This is my favorite complexity theoretic rant, that people sort of look at these things and say, well, gee, I'm doomed. I might as well pack and go home. And that's completely bogus. Next question to ask is, okay, how big do my inputs really get? And is that something I can handle? Okay, so is this exponential time threat something that I need to worry about? In the case of context-sensitive languages, it is, because my input is the program. And programs can get big. Okay, how big are your programs at this point? What's that? A couple of hundred lines. Yeah, by the end of this term, you might be at 1,000 lines or so. That's not small, right? That's not too small. But of course, they could get much larger than that. So now, for program size things, asymptotic complexity does matter. So we will fall back on this sort of an approach, and we'll do the context-free parsing, which you guys have done already. So I want to talk about context-sensitive checking. What we'll do is we'll take the grammar rules and we'll associate actions with them. Okay? We'll propagate information around the grammar rules using attributes. Okay? And an attribute intuitively can be anything that we care about. You care about the name of an identifier? Sure, I'll tell you what it is. You care about the value of an integer constant? Sure, that can be an attribute. You care about, what other things might we care about? I mean, you guys have written some C++ test cases. What other things might we care about? You had a question earlier about this. The scope of a variable is something I might care about. suppose I want to generate code, which you will generate whether you want to or not. But suppose you want to. What kinds of things do you care about? You care about the location that a variable lives in, right? The memory location it's been mapped to. That can be an attribute. So an attribute can be anything. So what these attributes are, these attributes carry information about the entities in your program. They don't have to be variables. They can be expressions. They can be functions. The return type of a function is an attribute of that function. The start address of a function, the code for a function, is an attribute. So these attributes carry information about the entities in your program. And we'll use rules. I like music to my lectures. This is great. When you see a movie and the action heats up, the music comes on. So this is a clear sign that now the action's heating up, and we're getting to a really exciting part of the course. So we'll use rules to compute the values of these attributes. And since we already used the word rules to talk about grammar rules, we'll use the phrase semantic rules to talk about these things that deal with the context-sensitive processing. Okay? So you can have a parse tree. We know what parse trees look like. Each node in a parse tree is a grammar symbol, right? Variable or a non-terminal. If I take a parse tree and I put at each node the attributes associated with the symbol for that node, each grammar symbol has some attributes, right? And if I take a parse tree for some input, and at each node in the parse tree I associate the attributes for the grammar symbol, what I get is an annotated parse tree. And this annotated parse tree passes information around using semantic rules. And we use this information to do our semantic checking. So this is the high-level view of what's coming. Here are some of the attributes that we could have for an identifier. A name for an identifier, scope. If it's a local, then I might want to know whether it's a formal parameter or not, because that can influence where in memory I put it. If it's a formal parameter, then I'm constrained about where it can live. Its type, if it's an integer, if it's an array, then I care about how big the array is, not in C, but in other languages, maybe how many dimensions it has, etc. If it's a struct, then I care about the fields and their types, and so on. All of that stuff. Is that?
So we don't have structs.
You don't have structs. That's right. That's right. Maybe we should add structs. Oh, come on. So we're processing attributes, okay, and we're using semantic rules to pass information about attributes around. So so think of these as parse trees, okay, so or rather annotated parse trees. So at each node in the parse tree, I have a set of attributes corresponding to that grammar symbol, and I have semantic rules that say, here's how you compute the value of this attribute. Now, there are two ways in which I can compute the value of an attribute over here. The value of this attribute can depend on and be computed from the value at sibling nodes or at a parent node. Okay, so you have information that's coming from a side, and it's coming down the parse tree into this node. Okay, so that's one case. In this case, we said that attribute is inherited. Okay. Alternatively, I can have an attribute here whose value is computed using information below it in the parse tree, and it's passed up the tree. And if there's information flowing up the tree, then we say that that attribute is synthesized. Okay? Why do we care? We care because it affects the code that we put in. So I'm going to add code to the parser to compute and propagate these attribute values. And the way the code is put in, and the way that's going to influence how this information is passed along the tree. So here's a really simple example. Okay, here's my grammar for a little calculator. This is, I think, not too different from the calculator that Sam showed you guys. So this is a calculator, right? So I'm not actually going to generate code. I'm just going to go ahead and compute the values. So here's my attributes. The expression E, the expression non-terminal, gets an attribute val, or value. Now, let's just look at this, okay? This grammar rule says E goes to E plus E. But I want to actually compute the values associated with expressions. Intuitively, the value of this guy is computed by taking the value here, computing the value here, and then summing them together, right? The value for this guy is take the value for this and the value for this and multiply them together, right? But if I want to write down in code what it is that I'm summing, so I have to say something like, take the value of this one and the value of this one and sum them, and that's the value of this E node in the parse tree. Not, the E nodes are all different, right? Because the value of this E is computed from these guys. That's the reason for the subscripts. So it's not like the grammar has different variables E, E1, E2. The subscripts simply say, this is E, this is a different occurrence of E, and that's indicated by the 1. And this is yet another occurrence of the variable, and that's indicated by the subscript. Okay? So my semantic rule says that the value of this node in a parse tree is obtained by taking the value of this node in the parse tree. So this is what the nodes look like. Oh, I'm out of time. I'm sorry. I'll stop here. We'll pick up on this example, and we'll discuss this on Wednesday.